When the James Webb Space Telescope directed its gaze deep into the cosmos, what it uncovered sent ripples through the entire field of astronomy. For decades, scientists believed they had a relatively solid grasp of how black holes, galaxies, and cosmic structures came to be. Yet, in this moment, Webb revealed something that didn't just add detail to the picture, it tore the picture apart. The shock of James Webb's discovery becomes even more striking when we consider where it took place. The location was not just any random patch of sky. It was in the galaxy cluster Abell 744, a region already known for being one of the strangest and most complex structures in the observable universe. Astronomers often call it Pandora's cluster, and the nickname could not be more fitting. This colossal cluster, located about 3.5 billion light-years from Earth, is the chaotic result of at least 4 smaller galaxy clusters colliding and merging over the course of billions of years. The result is a tangled cosmic structure filled with shattered galaxies, streams of gas, tidal debris, and dark matter that stretches across millions of light-years. When astronomers first studied Abell 744 with the Hubble Space Telescope, it already looked bizarre, but Webb's sharper eye revealed an even more intricate landscape of cosmic chaos. To place Webb's discovery here, in such a famously strange environment, adds an entirely new layer of mystery to the story. One of the most fascinating things about Abell 744 is how it acts as a natural cosmic magnifying glass. Thanks to the immense mass of the cluster, its gravity bends and distorts the light of objects lying far behind it in a phenomenon called gravitational lensing. This effect allows astronomers to see galaxies from the earliest periods of cosmic history, galaxies that would otherwise be too faint and distant for even the most advanced telescopes to detect. This is precisely why Abell 744 has been one of the prime targets for both Hubble and James Webb. By staring through this cosmic lens, Webb was able to probe deeper into the young universe than ever before, capturing light that has been traveling across space for more than 13 billion years. But the shock came when Webb's sharp vision picked up not just faint, stretched galaxies, but an unusually bright quasar-like object that seemed to sit out of place in this vast tapestry of distorted cosmic structures. To understand why the discovery is so significant, we need to appreciate the scientific role of Abell 744. It is essentially a natural laboratory for testing our ideas about cosmology. The cluster itself is extraordinary. Its galaxies are ripped apart, its hot gas glows in X-rays, and invisible dark matter weaves through it like an unseen skeleton. But its real importance lies in its ability to reveal the distant universe. The lensed galaxies behind Abell 744 allow astronomers to study the conditions of the cosmos less than 1 billion years after the Big Bang. By comparing these young galaxies to later ones, scientists hoped to piece together the story of how cosmic structures grew over time. Yet, instead of neatly filling in that story, Webb's discovery within Abell 744 ripped the script wide open. The telescope saw not just a relic of normal galactic growth, but something so unusual it raised the question: were we wrong about the order in which the universe built itself? This location has also long carried an air of mystery because of its violent history. Galaxy clusters like Abell 744 are the largest bound structures in the universe, held together by gravity and containing thousands of galaxies, along with enormous amounts of hot plasma and dark matter. But Abell 744 isn't stable. It's the aftermath of multiple collisions between galaxy clusters, making it more like a crime scene frozen in time. The evidence of past collisions lies in its distorted shapes, arcs of light created by lensing, and the trails of matter torn free during gravitational battles. Scientists often describe this cluster as a train wreck in space, a place where the normal rules of cosmic organization have been disrupted by the sheer violence of merging giants. Against this backdrop of cosmic chaos, Webb's discovery of a seemingly naked supermassive black hole becomes all the more shocking. If anywhere in the universe might conceal such an anomaly, it would be here, in a cluster where the ordinary processes of galaxy formation have been twisted and mangled beyond recognition. Adding to the intrigue is the fact that Abell 744 is one of the most intensely studied clusters in the universe. NASA and ESA designated it as one of the primary targets in the Hubble Frontier Fields program, which aimed to use gravitational lensing to push Hubble to its limits. This program revealed thousands of distant galaxies, some among the faintest ever observed at the time. When Webb inherited this target, astronomers expected sharper images and perhaps the discovery of even fainter galaxies lurking behind the cluster. What they did not expect was a bright, quasar-like beacon that seemed almost disconnected from any surrounding galaxy. The fact that this discovery happened in such a famous and carefully scrutinized location only amplifies the shock. It suggests that even in regions we thought we understood well, the universe is still hiding secrets that overturn our most confident models. From the chaos of Abell 2744, as James Webb's instruments peeled back layers of time and distance, something extraordinary began to stand out. Among the warped arcs of galaxies and the faint glimmers of distant cosmic light, Webb spotted an unusually bright, quasar-like object shining from the early universe. This was not just another background galaxy magnified by gravitational lensing, nor was it a typical star cluster caught in the telescope's gaze. Instead, it was a beacon, an object radiating so much light that it instantly drew the attention of astronomers combing through Webb's data. Its brightness was deeply puzzling. At a time when the universe was still young and galaxies were small, faint, and slowly assembling, here was an object shining with the ferocity of billions of stars combined. The universe at this stage shouldn't have been able to produce such brilliance, and yet, there it was, demanding explanation. The object resembled what astronomers call a quasar, one of the most powerful and energetic phenomena in the cosmos. Quasars are fueled by supermassive black holes that gorge themselves on gas and dust, releasing torrents of energy as matter spirals inward. The light produced can outshine entire galaxies, making quasars visible across billions of light years. But what made this discovery so strange was not just its quasar-like appearance, it was the time and place in which it was found. The early universe, less than 1 billion years old, should not have had the conditions to form such a massive, luminous object. Stars were still assembling into galaxies. Elements heavier than hydrogen and helium were just beginning to form in meaningful quantities. And yet, Webb was showing us a cosmic lighthouse blazing from the darkness of deep time. When scientists first analyzed the object, they struggled to fit it into existing categories. Its brightness suggested it was powered by an enormous black hole. But where was the galaxy that should have surrounded it? Typically, quasars live in the centers of massive galaxies, their light emerging from the heart of a bustling stellar metropolis. Yet, this source appeared strangely isolated, almost disconnected from the kind of galactic environment that quasars usually inhabit. Webb's data showed that this wasn't simply a trick of lensing or distortion. It was genuinely unusual, unlike anything astronomers had cataloged before. What stunned researchers further was the clarity with which Webb detected it. Thanks to its unprecedented infrared sensitivity, the telescope could pierce through dust and reveal the earliest light in ways Hubble never could. Instead of faint smears that left scientists debating their true nature, Webb delivered an unmistakable signal. Here was a luminous, quasar-like object shining with an intensity that defied expectation. The object's spectrum, the cosmic fingerprint of its light, confirmed that it lay far back in time, in an era when objects like this were supposed to be impossible. This wasn't a case of mistaken identity. It was real, and it was demanding answers. The emergence of this bright source also carried profound implications for our understanding of cosmic history. If such a luminous object could already exist at this early epoch, then something about the way black holes and galaxies form must be very different from what our theories predict. Was this object a quasar without a home galaxy? Or was it a brand new category of cosmic phenomenon, something we had never even imagined? The possibility alone sent ripples of excitement and confusion through the scientific community. Every detail Webb revealed seemed to hint that our picture of the early universe is incomplete, that we are only scratching the surface of its true complexity. In many ways, the object's very existence was like a message sent across time. The universe was more resourceful, more unpredictable, and perhaps more chaotic in its youth than we dared to think. The idea that such brilliance could emerge so soon after the Big Bang raises questions that strike at the very foundation of cosmology. Were black holes forming earlier than galaxies? Could massive structures grow more quickly than our models allow? Or was there some hidden process at work, one we have yet to uncover? Whatever the answers may be, one fact was clear. The object had emerged as one of the most important astronomical discoveries of the decade. Astronomers wasted no time in giving this extraordinary object an identity. After careful analysis and confirmation of its unusual nature, they officially named it Abell 2744-QS01, though many now simply call it QS01 for short. The name itself carries layers of meaning. The Abell 2744 tag roots it firmly within its cosmic neighborhood, the infamous Pandora's cluster that has long served as a stage for some of astronomy's most dramatic revelations. The QSO stands for quasi-stellar object, the technical term for quasars, because these objects often resemble stars when first seen in telescopes, yet shine with a power far beyond anything a single star could ever produce. The one marks it as the first of its kind discovered in this location, a signal that it may not be the last. The name may sound clinical, but behind those few letters lies an enigma so great that it may one day redefine how we think about the relationship between galaxies and black holes. Giving this beacon a name was not merely an administrative act. It was a declaration that the astronomical community had stumbled onto something that demanded recognition and study. In science, to name something is to acknowledge its place in the catalog of the universe, to admit that it must be explained. By christening it QS01, astronomers were admitting that it was real, that it belonged to no existing box, and that it carried mysteries that could not be ignored. Names like this serve as reference points in the vast ocean of celestial data, and QS01 now stands as a fixed landmark, a lighthouse in the ever-expanding map of cosmic phenomena. But what makes QS01 so compelling is that it is more than just another quasar. Quasars, though fascinating, are not new to astronomy. The first ones were identified in the 1960s, and they quickly became one of the most studied categories of astronomical objects. They are understood to be powered by supermassive black holes surrounded by accretion disks of gas and dust, glowing as matter spirals inward. Yet QS01 seems to break away from the script. It carries the luminous energy of a quasar, yes, but it does not appear to be nestled within the safe, expected arms of a galaxy. Instead, it shines almost alone, like a stranded starship adrift in the darkness of deep time. Its lonely brightness is what elevates it above the thousands of quasars already documented. It is the fact that its context, or lack thereof, makes no sense within our current models. The naming of QS01 was also symbolic of the turning point Webb had given us. Before this discovery, telescopes had shown us countless galaxies filled with stars, each obeying the broad strokes of cosmological theory. But here was a reminder that the universe is not obligated to follow our assumptions. Webb did not just extend our vision, it revealed a challenge. QS01's existence was an interruption in the smooth narrative of cosmic evolution. Naming it gave scientists a focal point around which to gather their research, their hypotheses, and their debates. It became a test case, a question mark given a proper noun, inviting teams of astronomers around the globe to weigh in on what it might mean. The story of QS01 also highlights how astronomy often works in layers. The object wasn't discovered in a dramatic single moment, but emerged gradually as Webb's instruments processed data, spectra were analyzed, and patterns were recognized. At first glance, it might have seemed like a particularly bright source magnified by lensing. Only when the details were sifted through, its distance, its brightness, its apparent isolation, did the full strangeness become clear. The naming of QS01 marked the moment when curiosity transformed into recognition, when whispers of something odd became a firm statement. This is not just unusual, it is unprecedented. What makes QS01 all the more haunting is the timing of its light. When Webb observed it, the photons reaching its detectors had been traveling for over 13 billion years. That means the object existed less than 1 billion years after the Big Bang, during an era when the first galaxies were only beginning to take shape. To shine so brightly, with such intensity, during that formative time suggests that it harbors a black hole of immense size. But black holes of that magnitude were not supposed to exist yet, not in a universe so young. The name QSO1 thus carries with it not just identity, but paradox. How could something so massive, so luminous, and so seemingly unbound appear at such an early point in cosmic history? Astronomers quickly began referring to QSO1 as one of the most tantalizing cosmic anomalies yet found by Webb. Research papers started circulating, each proposing different explanations for how it came to be. Conferences buzzed with debates, as specialists in black hole physics, galaxy evolution, and cosmology tried to fit QSO-1 into their frameworks. The mere act of naming it gave these discussions a center of gravity. Instead of speaking abstractly about some strange, unexplained quasar-like source, scientists could point to QSO-1 as a concrete case study. It became not just a discovery, but a rallying point for the broader question of whether our models of the early universe need to be rewritten. QSO-1 also embodies the dual role of the James Webb Space Telescope. It is both a window and a disruptor. On one hand, Webb provides clarity. It allows us to see farther and sharper than ever before, bringing hidden objects like QSO-1 into view. On the other hand, it disrupts our confidence, forcing us to admit that what we thought was settled science may only have been a partial truth. The existence of QSO-1 in Abell 2.744 underscores this tension. The telescope did not just give us sharper images of what we expected, it revealed something we had not prepared for. And that is perhaps the most important part of science, not confirming what we already know, but exposing what we don't. At the core of QSO-1 lies the secret to its staggering brilliance, a supermassive black hole estimated to be about 50 million times the mass of our Sun. This hidden giant is the engine powering its dazzling light, the force that transforms it into a quasar-like beacon visible across billions of light years. To put that mass into perspective, our Milky Way's central black hole, Sagittarius A, weighs in at around 4 million solar masses. That means the black hole inside QSO-1 is more than 10 times larger than the monster at the heart of our own galaxy. And yet, it existed when the universe was still in its infancy, less than 1 billion years old. How could such a titan grow so quickly in a cosmos still taking its first breaths? That question lies at the heart of why QSO-1 is such a groundbreaking discovery. The sheer scale of QSO-1's black hole forces us to rethink what we know about black hole growth. According to established theory, black holes form when massive stars collapse under their own gravity, leaving behind remnants a few times to perhaps a few dozen times the mass of the Sun. Over time, these stellar mass black holes can grow by consuming gas, dust, and even other stars, eventually swelling into supermassive black holes millions or billions of solar masses in size. But that process is supposed to take billions of years. By contrast, QSO-1's central giant reached 50 million solar masses astonishingly early, implying either that black holes can grow much faster than we thought, or that they can be born already massive. What makes the black hole inside QSO-1 particularly astonishing is that it is not quietly hiding in the darkness. Instead, it is feeding voraciously, creating an accretion disk, a swirling whirlpool of gas and dust spiraling into oblivion. As material falls inward, it heats up to extreme temperatures, emitting torrents of radiation that span the electromagnetic spectrum, from X-rays to visible light to infrared. This process produces the immense glow that makes QSO-1 appear so bright, even from billions of light years away. In effect, the black hole is cloaked in a storm of fire, a paradoxical reality where one of the universe's darkest objects becomes one of its brightest. Yet behind this spectacular glow lies a haunting truth. The black hole itself cannot be seen. Its event horizon, the boundary beyond which nothing escapes, remains forever invisible. What Webb observed is the furious energy of matter being shredded and consumed at the edge of that abyss. It is a reminder of the paradoxical nature of black holes, that they are at once cosmic voids and cosmic beacons, devouring everything around them while announcing their presence to the universe with unimaginable radiance. For QSO-1, the brightness is not just a feature, it is a clue, pointing to the ferocity of the hidden giant at its core. Astronomers are baffled not only by the size of QSO-1's black hole, but also by the timeline of its existence. For it to have reached 50 million solar masses so soon after the Big Bang, something unusual must have happened. Did it form from the collapse of an enormous primordial gas cloud, bypassing the smaller stages of growth entirely? Or did it begin as a stellar black hole, and somehow consume material at breakneck speed, faster than models currently allow? Either explanation would demand revisions to our theories of cosmic evolution. If black holes can indeed leapfrog the slow processes of star and galaxy formation, then they may not be byproducts of galaxies at all, but rather seeds from which galaxies themselves grow. The discovery of this hidden giant also forces us to confront another mystery: the balance of order and chaos in the universe. Supermassive black holes like this one are typically thought to anchor galaxies, stabilizing their cores and influencing star formation across vast regions. Yet in QS01, the black hole seems to exist without a clear galactic host. That raises a profound question. Does a black hole need a galaxy to survive, or can it thrive on its own, feeding on the faint wisps of gas that drift through intergalactic space? If the latter is true, then black holes may be far more independent and versatile than we ever realized. Another remarkable detail is how QS01's black hole challenges our sense of scale. We often think of stars, galaxies, and black holes as distinct entities, each with its own evolutionary path. But here we see a blurring of boundaries. The black hole is not merely a feature of QS01, it is QS01, the source of its light, its identity, and its mystery. Unlike galaxies, which are sprawling collections of billions of stars, QS01 is essentially defined by a single gravitational monster. The very fact that Webb detected it across such a vast gulf of time and space underscores how overpowering its radiation must be. The black hole, hidden in one sense, is in another sense screaming its presence into the cosmos. To better grasp the enormity of this hidden giant, consider its gravitational reach. A black hole with 50 million solar masses would exert such immense gravity that stars, gas, and even light itself would be bound to its influence across many light years. If it sat at the center of the Milky Way, its gravitational pull would utterly reshape our galactic environment. And yet, according to Webb's data, QS01's black hole may not even be tied to a massive galaxy. It stands alone, an emperor without a kingdom, radiating power into the void. This discovery also highlights the importance of Webb's infrared vision. Traditional optical telescopes might have missed QS01 entirely, or mistaken it for a bright star. But Webb's instruments could detect its redshift, the stretching of its light caused by the expansion of the universe, revealing just how far back in time it truly was. Without this capability, the hidden giant might have remained just that, hidden, lurking undetected in the background of Abell 2744. Webb did not just reveal its glow, it placed it in its proper cosmic context, showing us that it existed at a time when such giants were not supposed to exist. The discovery of QS01's supermassive black hole already carried weight on its own, but what made it truly astonishing was the way it broke expectations. In our current understanding of the cosmos, black holes of this size are not supposed to roam freely or shine without a galactic stage around them. Instead, such giants almost always reside at the hearts of massive galaxies, surrounded by billions or even trillions of stars. They act as gravitational anchors, their immense pull shaping the structure of their galactic homes, stabilizing star systems, and feeding on the reservoirs of gas and dust within. The conventional narrative is clear. Galaxies form, stars are born, and at their centers, black holes slowly grow. Yet QS01 seems to stand defiantly outside of this script, existing as if to say, the rules you thought you understood do not apply here. Normally, when astronomers peer into the universe and find a quasar, they also see the faint glow of the galaxy that hosts it, even if the black hole is so bright that it drowns out much of the surrounding starlight. Careful analysis usually reveals hints of a galactic structure, arcs of stars, reservoirs of interstellar gas, or the gravitational patterns that betray a galaxy's presence. These environments provide the fuel that black holes require to grow. Dense star fields and rich supplies of gas falling into their gravitational grasp. The presence of a supermassive black hole without a galaxy is not just unusual, it is almost unthinkable. QS01's glaring light makes the absence of such a host even more conspicuous. Where, astronomers ask, is the galaxy that should be wrapped around it like flesh around bone? The expectation that supermassive black holes live inside galaxies comes not from guesswork, but from decades of observational evidence. The Milky Way has Sagittarius A at its core. The Andromeda Galaxy harbors a black hole perhaps 100 times larger. Giant elliptical galaxies, some hundrds of thousands of light years across, host black holes weighing billions of solar masses. Everywhere astronomers look, the relationship holds. Galaxies and black holes are partners, growing together, shaping each other's destinies. This has become one of the cornerstones of modern cosmology. To find QSO-1 blazing brightly in the early universe without any clear galaxy to call home is like finding the beating heart of a creature with no body around it. This is why the discovery rattles scientific expectations so deeply. If QSO-1 is truly a supermassive black hole existing without a galactic host, it suggests that our theories of cosmic evolution are incomplete. The assumption that black holes grow only as galaxies evolve may not be universal. Perhaps black holes can form first, and galaxies come later, clustering around them like moths drawn to a flame. If so, then the relationship between galaxies and black holes is not as simple as we thought. It is more dynamic, more fluid, and potentially far stranger. QSO-1 becomes a case study in cosmic independence, suggesting that the universe may have multiple pathways to building its largest structures. Breaking expectations in this way also forces astronomers to confront uncomfortable possibilities. Could QSO-1 be an outlier, a rare fluke that does not challenge the broader rule? Or could it be just the first of many such objects, waiting to be revealed as Webb continues to survey the skies? If the latter is true, then the very framework we use to explain the origins of galaxies might need rewriting. The neat progression, from stars to galaxies to black holes, may instead be a web of interwoven competing processes, where sometimes black holes seed galaxies and sometimes galaxies seed black holes. In other words, QSO-1 may not be breaking the rules at all. It may be revealing that there were no rules to begin with, only assumptions. Consider the timeline again. Less than 1 billion years after the Big Bang, the universe was still in a state of transition. Hydrogen and helium dominated, the first stars were beginning to enrich space with heavier elements, and galaxies were assembling into fragile, clumpy shapes. In such a turbulent environment, the idea of a lone supermassive black hole shining like a quasar defies the logic of structure formation. Yet, here it is, burning bright against the darkness of cosmic dawn. It suggests that the early universe was capable of producing anomalies that our equations struggle to describe. QSO-1's brilliance is more than light. It is a signal flare, reminding us that cosmic history is not as orderly as we once believed. The expectations QSO-1 breaks also ripple into how we interpret other data. Astronomers have long assumed that when we look at the faintest, most distant quasars, we are essentially looking at galaxies in their infancy, still growing, but already recognizable. QSO-1 tells us that assumption may be wrong. It suggests that some bright sources in the early universe might not be galaxies at all, but rogue black holes, existing independently or in ways we have yet to understand. This reopens old questions and demands new models. Are we misclassifying some of the brightest objects we've seen in cosmic dawn? Have we underestimated how quickly black holes can dominate their environments? The true strangeness of QSO-1 becomes undeniable when we arrive at the fact that this one doesn't follow the universal script. Unlike the countless quasars we've studied, unlike the supermassive black holes we've identified at the centers of great galactic cities, QSO-1 appears almost entirely alone. When astronomers analyzed Webb's high-resolution data, they expected to find at least faint traces of a host galaxy wrapped around this brilliant core. Perhaps a halo of stars, a faint glow of starlight, or distorted arcs that could betray a surrounding structure. But none of these expected signatures emerged. What Webb revealed instead was an isolated, blinding source, unaccompanied by the visible evidence of a galactic home. It was as if someone had placed a cosmic lantern in the middle of the dark, without the house that should have contained it. This absence of a galaxy is not a minor detail. It is the heart of the enigma. For decades, astronomers have accepted as near fact that galaxies and black holes are symbiotic, growing together in ways that are inseparably linked. Galaxies provide the black hole with fuel in the form of dense gas and stars, while the black hole regulates galactic growth by releasing powerful winds and radiation that shape how stars form. Remove one from the other, and the whole framework of cosmic evolution begins to unravel. Yet, QSO-1 stands as a luminous contradiction, a quasar-like beacon radiating with all the fury of a supermassive black hole, but without the galactic structure that theory says must be there. Some astronomers initially speculated that perhaps the host galaxy was simply too faint or too diffuse for even Webb to see. After all, galaxies in the early universe were often small, clumpy, and irregular compared to the vast, well-formed spirals and ellipticals we know today. But the problem is that QS01's black hole is so massive that it should require a correspondingly massive galaxy to sustain it. A black hole 50 million times the mass of the Sun is not supposed to form or survive in isolation. It should sit in the bustling hub of a large stellar system. The fact that Webb could detect its light so clearly, but not the stars that should surround it, suggests either that the galaxy is extraordinarily faint, or that it does not exist in the way we expect at all. The image is haunting. A supermassive black hole blazing brightly, but stripped of the cosmic city that should define its existence. It brings to mind the idea of an emperor without a throne, or a heart without a body. If galaxies are the skeletons of the universe, then QS01 seems to be the fleshless heart, pumping energy into the void but lacking the framework that should hold it together. The loneliness of this object speaks volumes, suggesting that there are ways for black holes to shine without the safety net of a galactic host. If QS01 is truly alone, it would force us to reconsider whether black holes need galaxies at all. Could it be that black holes sometimes exist first, forming as independent titans from the direct collapse of primordial gas clouds in the early universe? Could they then serve as the gravitational seeds around which galaxies later form, flipping our understanding of cosmic chronology? Or perhaps QSO1 once had a galaxy, but some violent process, such as a catastrophic merger or gravitational ejection, tore it away, leaving only the black hole behind. Either scenario would revolutionize our picture of the early cosmos, suggesting that black holes are not merely byproducts of galactic evolution, but potentially architects of it. The absence of a galaxy also raises an unsettling thought. What if QS01 is not an isolated case? If Webb can find one such object, then there may be countless others hidden in the depths of the cosmos, supermassive black holes that glow fiercely but carry no visible galactic signature. That would mean the universe contains far more free-floating or faintly hosted black holes than we ever anticipated, scattered like lonely titans across intergalactic space. The discovery of even a handful more would topple long-standing assumptions about how matter organizes itself on the largest scales. Astronomers are cautious, of course. They acknowledge the possibility that QS01's galaxy is present, but simply too dim for current instruments to detect. If so, it might mean that QS01 is not truly breaking the rules, only pushing them to their limits. Yet the fact remains that Webb's extraordinary sensitivity, which can reveal galaxies billions of times fainter than the human eye could ever see, has not yet shown a convincing host around this object. That silence, that absence, echoes louder with every passing observation. The possibility that QS01 is genuinely alone remains very much alive, and with it, the potential to reshape the foundations of cosmology. And so, QS01 stands out not merely because of its brightness, but because of its context, or more precisely, its lack of one. It appears as though the cosmos has presented us with the skeleton of a mystery, daring us to imagine how such a thing could exist. Alone in the vast theater of Abell 744, QS01 shines without the company of a galactic chorus, a solo performance that defies the ensemble we expected to see. It is this loneliness, this lack of a galactic embrace, that makes the discovery not just strange, but revolutionary. Astronomers, grasping for the right words to capture QS01's bizarre nature, began to describe it as a naked black hole, a supermassive giant stripped of its cosmic home, laid bare against the backdrop of the early universe. The term is both evocative and unsettling. Black holes are usually thought of as hidden creatures, cloaked in the dense environments of galaxies, their power veiled by the starlight, dust, and gas that surround them. But QS01 seems to defy that expectation entirely. It shines brightly without the veil, its fury exposed, its gravitational hunger unmasked. To call it naked is to recognize that it lacks the usual protective clothing of a galaxy, standing in stark defiance of the structures that should normally cradle such a colossal force. This idea of a naked black hole pushes us into uncharted territory. For decades, Black holes have been understood through the lens of their symbiotic relationship with galaxies. They are the unseen anchors at galactic centers, cloaked by billions of stars and nourished by dense supplies of interstellar gas. QSO-1 shatters that narrative. Its nakedness suggests a black hole that either never had a galactic host or lost it somewhere along the way, leaving behind a luminous engine running without its machine. If true, it would mean that the connection between black holes and galaxies is not as absolute as scientists once believed. Instead, black holes might be capable of existing in a state of shocking independence, sustained by processes we have yet to fully understand. The metaphor of nakedness also underscores the vulnerability of our theories. To find a supermassive black hole stripped of its cosmic home is to expose the fragility of our assumptions about the universe. We have long assumed that galaxies and black holes were inseparable, that the one could not exist without the other. QSO-1 forces us to confront the possibility that nature operates with greater variety than our models allow. The universe, in other words, has no obligation to clothe its black holes and galaxies simply because our equations prefer it that way. But how does a black hole become naked? There are several possibilities, each carrying profound implications. One scenario is that QSO-1 formed directly from the collapse of an enormous gas cloud in the early universe, skipping the stages of star formation and galactic assembly entirely. In this case, the black hole would never have had a galaxy to call home. It would have been born naked, a primordial titan blazing into existence without the trappings of stars. Another possibility is that QSO-1 once had a galaxy, but lost it through cosmic violence. A galactic merger or gravitational interaction with another massive system could have torn away its stars, leaving the black hole wandering alone in intergalactic space. If so, then the nakedness of QSO-1 tells a story of catastrophic loss, of a black hole stripped down to its essence by the violence of the cosmos. There is also the more cautious explanation, that the galaxy is there, but simply too faint for us to see. Perhaps it is composed only of dim, ancient stars, or its light has been so stretched and smeared by distance and lensing effects that even Webb's extraordinary sensitivity cannot detect it. If this turns out to be the case, QSO-1 may not be truly naked, only dressed in clothes so thin and fragile that they escape our vision. Yet, even this scenario would stretch our understanding, because a black hole of this size should, by all rights, demand a substantial galaxy to fuel its growth. The absence of a visible host remains one of the loudest silences in astronomy today. The notion of a naked black hole also resonates on a philosophical level. Black holes are already among the most mysterious entities in the cosmos, regions where gravity is so extreme that not even light can escape, where space and time themselves are warped beyond recognition. To imagine one existing in isolation, stripped of its galactic context, is to confront the raw power of nature at its most elemental. QSO-1 is not softened by the beauty of starlight or hidden within a galaxy's graceful arms. It is stark, raw, and unapologetically alien. It is a reminder that the universe's deepest mysteries are not always clothed in comforting forms. They can be laid bare, daring us to stare directly into their naked strangeness. This framing of QSO-1 as a naked black hole also reframes our sense of cosmic order. For so long, astronomers have treated galaxies as the universe's fundamental units, the great cities of stars that build the architecture of the cosmos. But QSO-1 suggests that black holes themselves might be the more primal structures, capable of existing independently even when galaxies do not. If naked black holes are real and not just rare anomalies, then the hierarchy of cosmic formation may need to be rewritten, with black holes at the foundation rather than the periphery. The strangeness of QSO-1 doesn't lie only in its brilliance or its massive black hole. It lies in the fact that, according to every dominant theory in astrophysics, it shouldn't exist like this at all. Our models of the universe tell us that supermassive black holes and galaxies are bound to one another in both origin and growth. The galaxies provide the raw material, gas, dust, and stars, that black holes consume to grow into titans millions or billions of times more massive than the Sun. In turn, black holes regulate the growth of galaxies, releasing outflows of energy that shape how stars form. This is not just a minor correlation, it is one of the cornerstones of modern cosmology. When you look into the heart of a galaxy, you expect to find a black hole. When you see a quasar, you expect to find a galaxy wrapped around it. That is the order we believe the universe followed. Yet QS01 stands alone, a glowing anomaly that says, what if that order isn't universal? The theoretical problem is immediate and profound. Black holes, in their traditional life cycle, are supposed to emerge as the corpses of massive stars. These stellar mass black holes begin relatively small, perhaps a few to a few dozen solar masses. Over time, through processes like mergers and steady accretion, they can grow larger. Some of them, under the right conditions, can balloon into supermassive black holes reaching millions or billions of solar masses. But this growth is supposed to take time. Billions of years, in fact. Galaxies act as the cosmic cradles where this process can unfold, providing the gravitational well and fuel supply necessary to feed the black hole. The presence of a galaxy is not just expected, it is essential. Without it, the black hole has nothing to eat, no way to grow into the kind of monster we now see in QS01. Yet here we are, staring at a black hole 50 million times the mass of our Sun in an era when galaxies themselves were still fragile, clumpy, and only beginning to take shape. That contradiction is why scientists call QS01 so strange. It suggests that the story of cosmic growth is either incomplete or, worse, fundamentally flawed. If black holes can indeed grow to such enormous sizes without galaxies, then our models of structure formation, the very story of how the universe assembled itself from the chaos of the Big Bang, must be rewritten. Consider how tightly black holes and galaxies are thought to be linked. Observations have shown that the mass of a galaxy's central black hole is often proportional to the mass of the galaxy's bulge of stars. This correlation, known as the M-sigma relation, has been one of the strongest pieces of evidence for the co-evolution of galaxies and black holes. It implies a deep, physical connection. Galaxies and black holes do not just coexist, they grow together, influencing one another's development. QS01 shatters this symmetry. If it truly has no host galaxy, then the M-sigma relation might not be as universal as we believed. The link between galaxies and black holes may be statistical rather than fundamental, with exceptions that carry far greater weight than the rule. The strangeness of QS01 also lies in its timing. Less than 1 billion years after the Big Bang, the universe was still in what astronomers call the cosmic dawn, the period when the first stars and galaxies were just beginning to illuminate the darkness. Galaxies at this stage were small, irregular, and faint. They lacked the heavy elements needed to form complex structures, and they certainly weren't supposed to host black holes tens of millions of solar masses in size. According to conventional models, the universe simply hadn't had enough time to build something like QS01. Its existence is therefore not just unusual, it is a direct challenge to the timeline of cosmic history. This is why QS01 is so strange. It seems to represent a reality where the sequence of cosmic formation is reversed. Instead of galaxies forming first and black holes following, QS01 hints at the possibility that black holes might sometimes come first. In such a scenario, massive black holes could serve as gravitational seeds, pulling matter toward them and eventually building galaxies around their immense gravity wells. This flips our entire understanding upside down. If black holes can exist independently, then galaxies may not be the primary building blocks of the universe after all. They might instead be secondary structures that form in response to black holes. The implications ripple outward in every direction. If QS01 is not unique, then we may need to accept that a significant number of black holes in the early universe did not follow the rules. That would mean the population of naked, or nearly naked black holes is larger than we thought, raising new questions about how common these objects are and what role they played in shaping the universe. Did they contribute to the ionization of the cosmos, the period when the first sources of light cleared the fog of hydrogen gas left after the Big Bang? Did they influence the growth of early cosmic structures in ways we haven't accounted for? Adding to the strangeness is the fact that QS01 is not faint or subtle. It is blazing with a brightness that Webb could detect across billions of light years. Its nakedness is not hidden but glaring, forcing astronomers to acknowledge it. It is not an object that can be dismissed as a statistical outlier or explained away by observational error. It is a clear, undeniable reality that contradicts our expectations. That starkness, that refusal to fit into the models, is part of what makes QS01 so unsettling. Even if future observations reveal that QS01 does have a faint galaxy hidden beneath its light, the mystery does not disappear. The galaxy would still have to be far too small and faint to explain the presence of a 50 million solar mass black hole. In that case, the strangeness shifts from, how can a black hole exist without a galaxy? To, how can such a massive black hole exist in such a tiny galaxy? Either way, the discovery defies the tidy frameworks of theory and leaves us grappling with the unsettling truth that our cosmic story is incomplete. For decades, astronomers have relied on what we might call the old story of black holes, a narrative built from decades of observations and theories that seem to neatly explain their origins and growth. In this account, black holes begin their lives as the remnants of massive stars. When such a star exhausts its nuclear fuel, it can no longer support itself against gravity. Its core collapses inward, crushing atoms into a point of infinite density, and in that collapse, a black hole is born. These stellar mass black holes, weighing anywhere from a few to perhaps a few dozen times the mass of our Sun, are scattered throughout galaxies like seeds awaiting nourishment. Over time, they grow by swallowing surrounding material, gas clouds, dust, and even other stars, slowly fattening into the behemoths we call supermassive black holes. According to this story, galaxies play an essential role. They are the ecosystems in which black holes thrive, providing both the raw material for feeding and the gravitational framework that keeps everything together. The galaxy's central regions are rich with dense gas and star clusters, perfect fuel for a hungry black hole. As matter falls inward, it heats up, forming an accretion disk that glows brilliantly and, in extreme cases, powers quasars. This relationship was thought to be universal. Where there is a galaxy, there is a central black hole, and where there is a black hole, it is because a galaxy has nurtured it. The two grow hand in hand, influencing each other's fates. The old story is reinforced by a wealth of observations. Nearly every large galaxy studied has been found to harbor a supermassive black hole at its core. In the Milky Way, Sagittarius A sits like a cosmic monarch, weighing in at about 4 million solar masses. In Andromeda, its central black hole is closer to 100 million solar masses. Giant elliptical galaxies at the centers of galaxy clusters host black holes billions of times the mass of the Sun. Everywhere astronomers look, the same pattern emerges. Black holes are nestled inside galaxies, and the size of the black hole seems tightly correlated with the size of its host. This correlation is so consistent that scientists developed scaling laws like the M-sigma relation, which describes the proportionality between a galaxy's central black hole and the velocity of its stars. It was one of the clearest pieces of evidence that galaxies and black holes are codependent, evolving together across cosmic time. The narrative also fit neatly into the cosmic timeline. The first stars exploded, creating black holes. Galaxies formed as clouds of gas collapsed, and inside them these small black holes began to grow. Over billions of years, galaxies merged, gas funneled inward, and black holes ballooned to supermassive sizes. Occasionally, when a black hole consumed matter especially quickly, it ignited as a quasar, shining so brightly that it could be seen across the universe. But always, the quasar was tied to a galaxy, the light emerging not just from the black hole itself, but from the accretion processes happening within its galactic environment. This old story was satisfying because it created a sense of order in the universe. It explained why every galaxy seemed to have a black hole, and why the largest black holes were found at the centers of the largest galaxies. It accounted for the growth of structure over time, showing how small beginnings could lead to grand cosmic cities. It also suggested that the universe was predictable, that, given enough time, the same processes would always play out in the same way. But QS01's existence tears at the fabric of this old story. Its supermassive black hole, 50 million solar masses strong, appears in the early universe, when galaxies were still young and fragile. Its quasar-like light blazes without a clear galactic home. If the old story were complete, QS01 should not exist. There simply hasn't been enough time or enough galactic structure for such a black hole to have grown through the gradual processes of stellar collapse, accretion, and mergers. The old story requires billions of years to produce such a giant, but QSO-1 emerges less than 1 billion years after the Big Bang. The timeline doesn't match. The framework doesn't hold. The contrast between QSO-1 and the old story is stark. On one side, we have a comforting, ordered vision of black hole growth, with galaxies as nurturing parents guiding their children into maturity. On the other, we have a lone, naked giant in the early universe, blazing with impossible brilliance, as if it skipped ahead in the cosmic script. The old story accounts for most of what we see in the nearby universe, but QSO-1 reminds us that what works here and now may not apply everywhere and always. And so, the old story is not discarded but destabilized. It remains a useful framework for explaining much of what we observe in mature galaxies today, but its limits are now exposed. QSO-1 forces us to admit that the narrative of black hole growth is more complex, with alternative paths that allow giants to emerge outside the rules we thought were ironclad. The universe, it seems, tells multiple stories at once, and the old one is only a chapter, not the book itself. QSO-1 doesn't just stretch the old story, it breaks it wide open. The supermassive black hole at its heart seems utterly disconnected from the well-established process by which such giants are supposed to form and evolve. In the framework astronomers have relied on for decades, black holes of this magnitude are the outcome of long, gradual growth inside galaxies. They begin small, from the collapse of massive stars, and slowly expand by consuming gas, dust, and other stars within their galactic neighborhoods. Galaxies act as both nurseries and fuel depots, providing the rich environments needed for black holes to grow into titans. Yet QSO-1 refuses to play by these rules. Here we see a 50 million solar mass black hole, blazing with quasar-like intensity, but without any sign of a galaxy wrapped around it. It is as though the universe skipped several chapters of the story and dropped us straight into a scene that should not exist. The disconnection is what makes QSO-1 so radical. It is not simply an oddity of brightness or timing. It is a direct contradiction of the mechanisms we thought were required for black holes to achieve such size. According to the old story, a black hole of this mass should sit in the bustling center of a galaxy, drawing material inward from dense star clusters and gas clouds. It should be surrounded by billions of stars, its presence mirrored in the scale and shape of the galactic bulge around it. Yet Webb's sensitive instruments reveal no such galactic companion. Instead, they show us an isolated beacon, as though the black hole has been cut loose from the very ecosystem it was supposed to depend upon. This disconnection forces us to confront a possibility we've long resisted. Maybe the story we've told about galaxies and black holes growing hand in hand is incomplete, or even fundamentally flawed. QSO-1 seems to exist outside of that narrative, suggesting there may be alternate routes to creating supermassive black holes, routes that bypass galaxies entirely. In this way, QSO-1 does not merely extend the old story, adding a strange new chapter. It undermines the very structure of the story itself, like a plot twist that rewrites everything we thought we knew about the characters and their roles. Imagine the implications of such a break. If QSO-1 formed without a galaxy, then black holes may not be secondary players in cosmic evolution, but primary ones. Instead of being nurtured by galaxies, perhaps they serve as the seeds from which galaxies grow. In that inverted story, the black hole comes first, exerting its immense gravitational pull to draw in matter, and only later does a galaxy assemble around it. QSO-1's existence hints at this reversal, suggesting that we may have misunderstood the order of events in the universe's earliest epochs. If galaxies are not the indispensable cradles we assumed, then the entire history of structure formation may need to be reconsidered. The breaking of the story also raises uncomfortable questions about how many other QSO-1-like objects might be out there. If Webb could detect one naked, galaxyless black hole in a single region of the sky, could there be many more waiting to be found? If so, then the exceptions might not be rare anomalies but common realities of the early universe. That would mean our carefully crafted models, designed to explain the slow and steady growth of black holes inside galaxies, have overlooked an entire population of cosmic phenomena. The break isn't just about one object. It's about the possibility of a hidden pattern we've never accounted for. Scientists have, of course, considered alternative growth scenarios for black holes. Some theories suggest that the very first black holes could have formed not from stars, but directly from the collapse of enormous gas clouds in the early universe, creating giants from the start. Others propose that small black holes could grow incredibly fast under special conditions, accreting matter at rates far higher than previously thought possible. But QS01 doesn't just support one of these alternatives. It forces us to take them seriously. Its disconnection from the expected galactic framework is a flashing warning sign that our standard model is inadequate on its own. The symbolism of this break cannot be overstated. The old story gave us comfort because it was orderly. Stars give rise to black holes. Black holes grow within galaxies. Galaxies and black holes co-evolve in lockstep. QSO1 disrupts that symmetry. It shows us that the universe is under no obligation to follow our tidy narratives. The cosmos is messy, chaotic, and full of surprises. Just when we think we've understood its logic, it presents us with something that tears the script apart. In this sense, QSO1 is not just an astronomical discovery. It is a philosophical challenge, reminding us that science is always provisional, always subject to revision in the face of new evidence. The break also invites us to look backward at what we thought we understood. How many other objects, previously dismissed as anomalies or too faint to study, might actually represent black holes like QSO1? Could some of the quasars we've cataloged in the early universe also be galaxyless giants, hiding in plain sight because we assumed they had galaxies too faint to detect? Webb's discovery forces us to revisit old data with new eyes, questioning whether our interpretations were shaped more by the comfort of our theories than by the reality of what was there. QSO1's mystery deepens when we place it in its proper cosmic timeline. To make things harder for our theories, it appeared when the universe was still young, less than 1 billion years after the Big Bang. That era, often referred to as the Cosmic Dawn, was supposed to be a time of beginnings, not of completed marvels. Stars were just igniting for the first time. Galaxies were fragile clumps of gas and dust, irregular and faint. Heavy elements like carbon, oxygen, and iron were only beginning to emerge from the deaths of the first generation of stars. This was not a universe expected to harbor giants. And yet, here we find QSO1, blazing with the power of a 50 million solar mass black hole, standing as a cosmic skyscraper in a world still learning how to build huts. This is the core of the early universe puzzle. How can something so massive, so luminous, and so seemingly independent exist at such a young age in cosmic history? Our models of structure formation suggest that galaxies and black holes need billions of years to grow to this scale. Even under the most optimistic scenarios, where black holes consume matter at their maximum allowed rate, a limit known as the Eddington limit, it would take far longer than 1 billion years to reach the size Webb observed in QSO1. The fact that it appears fully formed at such an early epoch is like discovering a towering oak tree in a forest where the seeds were only just planted. To appreciate how baffling this is, we need to consider the timeline of the universe itself. The Big Bang happened about 13.8 billion years ago. For the first few 100 million years, the universe was a dark, opaque place, filled mostly with hydrogen gas. Then came the birth of the first stars, massive, short-lived giants that lived fast and died young, exploding as supernovae and seeding the cosmos with heavier elements. From these first stars, small galaxies began to assemble. This is what scientists expected to see when peering into the early universe with Webb: fragile, clumpy galaxies, faintly glowing as the earliest building blocks of cosmic structure. Instead, QSO1 presents us with something that should belong to a much later chapter: a massive, fully active black hole, devouring matter and blazing like a quasar. This puzzle forces us to ask whether our models of black hole growth are missing something fundamental. Perhaps black holes can form much larger at birth than we thought. Instead of starting from the collapse of stars just a few times more massive than the Sun, maybe the early universe allowed for direct collapse black holes, forming instantly with masses of tens or even hundreds of thousands of suns. From there, it would not take long for them to grow into supermassive giants like QSO1. Alternatively, perhaps the rules of accretion, the rate at which black holes consume matter, are more flexible than we assumed. If early black holes could feed faster than the Eddington limit suggests, they might have been able to balloon into giants in just a few 100 million years. The timing also carries implications for the larger story of the universe's evolution. The period when QS01 existed was a pivotal one, known as the Epoch of Ionization. During this era, the first galaxies and quasars released enough light to ionize the hydrogen that filled the cosmos, transforming it from an opaque fog into the transparent universe we see today. If objects like QS01 existed in significant numbers, they could have played a crucial role in driving this transformation. Their intense radiation may have been instrumental in lifting the cosmic veil, allowing starlight to travel freely through space. In other words, black holes like QS01 may not just be anomalies, they may have been key players in shaping the universe's fundamental properties. But the puzzle is not just about physics, it's also about numbers. If QS01 is one of many such objects, then the early universe may have been littered with naked or nearly naked black holes, each blazing like a quasar. If so, then the early cosmos was far more energetic and chaotic than our models suggest. On the other hand, if QS01 is truly unique, then we are left with a different puzzle. Why did this one black hole defy the odds and grow so quickly when the rest followed the slower, expected path? Either scenario is deeply unsettling. If it's common, our theories are too narrow. If it's rare, then our understanding of statistical probabilities and cosmic evolution may be flawed. Another layer of strangeness comes from QS01's environment. Being found in Abell 2744, a cluster famous for its collisions and complex gravitational lensing, raises the question of whether the cluster's chaotic conditions somehow contributed to QS01's early growth. Could the merging of galaxies and the violent exchange of matter in such clusters accelerate black hole growth in ways we haven't modeled? Or did QS01 predate the cluster entirely, existing before the galaxies of Abell 2744 collided to form the chaos we see today? If the latter is true, then QS01 predates not only galaxies, but even the structures that define galaxy clusters themselves, making it even more mysterious. The early universe puzzle isn't just a technical problem for astronomers, it's a blow to the confidence we place in our cosmic timeline. For years, we believed we understood the sequence: the Big Bang, the first stars, the first galaxies, and then the slow emergence of supermassive black holes. QS01 shatters that sequence. It shows us that the universe was capable of producing giants almost immediately, leaving us scrambling to understand how. If the story of the cosmos is a book, then QS01 is a chapter that appears out of order, a revelation that suggests the narrative is not as linear as we assumed. And perhaps that is the most humbling part of the puzzle. QS01 forces us to admit that we are still in the infancy of understanding the cosmos. We may have mapped galaxies, measured cosmic microwave background radiation, and traced the expansion of the universe, but discoveries like this remind us that the universe still holds surprises that defy the frameworks we construct. The fact that QS01 appeared less than 1 billion years after the Big Bang is not just an observational oddity. It is a challenge, a provocation from the cosmos itself. It is as if the universe is saying, "You thought you had my story figured out, but you've only just begun." The question that QS01 forces us to confront is as unsettling as it is profound. Did it form first? Could black holes actually come before galaxies, reversing the order we always assumed? This idea cuts directly against the grain of the traditional cosmic narrative, yet the existence of QS01 makes it impossible to ignore. For decades, galaxies were treated as the foundational building blocks of the universe, great cities of stars that structured the cosmos, with black holes growing quietly at their centers as byproducts of galactic life. But QS01 hints at an alternate possibility, that in the early universe, black holes may have formed independently, perhaps even serving as the gravitational seeds around which galaxies later assembled. If true, this would upend one of the most cherished assumptions in modern cosmology. The notion that black holes might come first is not entirely new. Theoretical astrophysicists have long speculated about the possibility of direct collapse black holes, giants born not from stars but from the collapse of immense primordial gas clouds. Unlike stellar mass black holes, which form as the corpses of massive stars, direct collapse black holes could have begun their lives with hundreds of thousands or even millions of solar masses. If such objects formed during the universe's earliest epochs, they would instantly leap ahead of the slow, gradual growth outlined in the traditional model. From there, It would be a relatively short path to becoming the supermassive black holes we now see in quasars like QS01. But what makes QS01 compelling is that it is not just theoretical. It is observational evidence that supports this radical idea. Here is an object less than 1 billion years after the Big Bang, already boasting a black hole 50 million times the mass of the Sun, but without a galaxy to explain its growth. If galaxies truly came first, QS01 should not exist. If black holes can come first, then QS01 is exactly what we would expect. A primordial giant blazing long before galaxies had time to form in full. In this light, QS01 may not just be an anomaly, it may be the first clear proof that black holes were the universe's original architects. This reversal of order has staggering implications. If black holes can form before galaxies, then galaxies themselves may not be the primary building blocks of the cosmos. Instead, black holes may have acted as the scaffolding around which galaxies grew. Their immense gravity could have pulled in matter, catalyzing the formation of stars and assembling galaxies in their orbits. In this scenario, galaxies are not the cradles of black holes. They are the children of black holes. The entire cosmic hierarchy shifts, with black holes taking on a far more central role in the universe's story than we ever imagined. Such a reversal would also help explain some of the long-standing puzzles in cosmology. For instance, astronomers have long been surprised by the discovery of quasars in the early universe that shine with the brilliance of billions of suns. According to the old model, there simply wasn't enough time for black holes to grow so large, so fast. But if black holes could form directly as giants, before galaxies even existed, their presence in the early universe is no longer an impossibility. It is an inevitability. QS01 becomes a missing puzzle piece that makes the picture clearer. The universe's first billion years may have been dominated not by fragile galaxies, but by naked black holes blazing alone in the darkness. Yet this possibility raises new questions that cut to the heart of physics itself. How could such direct collapse black holes form? What conditions would allow a primordial gas cloud to bypass star formation and collapse directly into a singularity? Some theories suggest that unusually dense pockets of hydrogen in the early universe, under the right conditions, could have collapsed under their own gravity without fragmenting into stars. Others propose that radiation from nearby regions could have suppressed star formation, allowing the gas to funnel directly into a black hole. If QS01 is truly a black hole that formed before its galaxy, then it may represent one of these long hypothesized pathways brought vividly to life. The reversal of order also challenges how we think about cosmic balance. In the standard view, galaxies and black holes regulate one another. Galaxies feed black holes, and black holes release energy that shapes the growth of galaxies. But if black holes came first, the relationship may have been far more one-sided in the beginning. Black holes could have dictated the very existence of galaxies, not merely influenced their growth. In this sense, QS01 is not just an oddity. It is a window into a universe where black holes were the original architects, and galaxies were the structures they built. There is also a sobering reminder hidden in this question. Perhaps our very categories of first and second are too simplistic for the cosmos. The universe may not follow a single linear progression, where stars lead to galaxies and galaxies lead to black holes. Instead, it may have multiple pathways, some where galaxies form first and others where black holes do. QS01, in this view, is evidence of one such alternate path, a branch of cosmic evolution that runs in parallel to the one we thought was universal. The question, did it form first, may not have a single answer. Sometimes black holes came first, sometimes galaxies did. The universe, in its vastness, may have fit room for both stories at once. What makes QS01 so powerful is that it forces us to consider this possibility not as speculation, but as reality. Its existence asks us directly, are you ready to accept a universe where the giants of gravity existed before the great cities of stars? Are you ready to admit that the very order of cosmic creation may be different than you believed? For scientists, the answer must be yes, because QS01 leaves no choice. It is a glaring reminder that the cosmos is not bound to follow our preferred sequence of events. It writes its own order, and we must adapt to it. One of the most compelling ideas that astronomers have proposed to explain QS01 is possible explanation. 1. Maybe it formed directly from the collapse of a giant primordial gas cloud, skipping the usual steps of stars and galaxies entirely. In this scenario, the supermassive black hole at the heart of QS01 would not have begun as the corpse of a dying star, as in the traditional story. Instead, it would have been born fully massive, a direct collapse black hole created from the raw material of the early universe itself. If this explanation holds true, then QS01 is not simply an odd outlier, it is living evidence of an entirely different pathway for cosmic evolution, one that bypasses the messy trial and error process of star formation and jumps straight to the creation of a gravitational giant. The theory of direct collapse black holes has long existed as a way to solve the time problem in cosmology. As we've discussed, black holes formed from stars start out small, maybe a few dozen solar masses at most. To grow into the titans we see in quasars, they need billions of years of feeding. But quasars like QS01 appear less than a billion years after the Big Bang, far too soon for such a slow growth process to produce giants. Direct collapse solves this by proposing that in certain rare conditions, huge clouds of hydrogen gas in the early universe never fragmented into stars. Instead, under immense gravitational pressure, the entire cloud collapsed inward as one, skipping the intermediate stages and forming a black hole already weighing hundreds of thousands or even millions of solar masses. This shortcut would give the universe a head start, producing enormous black holes very early in its history. But how could such a direct collapse happen? Normally, when a gas cloud collapses under gravity, it breaks into smaller clumps that form stars. This process is regulated by cooling. As the gas compresses, it radiates energy, lowering its temperature and fragmenting into pockets of star formation. For a direct collapse to occur, this cooling must be suppressed. One way this might happen is if the gas cloud were bombarded by radiation from nearby regions, keeping it too warm to fragment into stars. Without stars to form, the cloud would remain whole until gravity forced it to implode in a single catastrophic collapse, birthing a massive black hole in one dramatic moment. If QS01 was born this way, it would explain why it appears without a visible galaxy. A direct collapse black hole doesn't need stars or galaxies to precede it. It creates itself from the universe's raw hydrogen, and only afterward might it serve as a seed for galaxies to grow around. In fact, such a process could flip our entire understanding of cosmic order. Instead of galaxies building black holes, perhaps black holes like QS01 built galaxies. They could have acted as gravitational anchors, pulling in matter and catalyzing the birth of the first galaxies around their immense cores. In this light, QS01 is not a mistake of timing, but a pioneer, one of the first giants to emerge in the young cosmos. The direct collapse scenario is also consistent with the sheer size of QS01's black hole. At 50 million solar masses, it is already far beyond what stellar collapse and normal accretion could plausibly achieve so early. But if it began as a direct collapse black hole with, say, a few million solar masses, then growing to 50 million in a few 100 million years becomes far more feasible. Instead of needing to consume matter at impossible rates, QS01 would simply have been born ahead of the curve, inheriting its massive size from the very moment of its creation. Still, this explanation, while elegant, comes with challenges. For one, direct collapse black holes require very specific conditions: pristine gas clouds free of metals, elements heavier than hydrogen and helium, suppression of cooling and star formation, and isolation from disruptive forces. Were such conditions common enough in the early universe to produce not just QS01, but the many other quasars we've already observed from that era? If direct collapse was rare, then QS01 might be an exceptional case. But if it was common, then we may have underestimated how many of the universe's earliest structures were shaped by these colossal shortcuts. Another challenge lies in confirming this process observationally. Black holes, by their nature, cannot be seen directly, and the galaxies they might eventually seed could be faint or invisible at cosmic distances. Distinguishing a direct collapse black hole from one that grew rapidly by other means is extraordinarily difficult. But QS01's nakedness, the absence of a clear galaxy, offers one of the strongest clues that direct collapse may indeed be what happened. If it had formed in a galaxy, we would expect to see at least some trace of that galaxy. Instead, we see only the blazing signature of the black hole itself, standing alone in the cosmic void. If QSO-1 was indeed born from the direct collapse of a primordial gas cloud, then it stands as a fossil of cosmic innovation, proof that the universe's first billion years were more creative and chaotic than we dared to imagine. It reminds us that the rules we write, the sequences we assume, may only describe part of the story. Nature, in its rawest form, may have had more than one way to create giants. QSO-1's brilliance would then be the light of a black hole that skipped the long journey, choosing instead to leap straight to the endgame. Another provocative idea that astronomers have put forward is possible explanation 2. QSO-1 might not have been born alone at all. Instead, it could have once belonged to a galaxy, only to be violently thrown out after a colossal cosmic collision. In this scenario, the supermassive black hole did not defy the rules of galaxy-black hole coevolution in its origin. It followed them, until a catastrophic event rewrote its destiny. Now, stripped of its stellar home, it wanders through the universe nearly alone, blazing like a rogue titan in the void. This explanation turns QSO-1 into the ultimate cosmic exile, a gravitational monarch dethroned and cast adrift after a galactic war. The mechanism for such an ejection is not entirely speculative. Theoretical models and simulations show that when galaxies merge, their central black holes are drawn together by gravity, forming binary or even trinary black hole systems. These systems eventually coalesce, releasing enormous bursts of gravitational waves, the ripples in spacetime first predicted by Einstein and finally detected by LIGO in 2015. But conservation of momentum dictates that when these black holes merge, the newborn giant can be kicked by the asymmetric blast of gravitational radiation. If the kick is powerful enough, it can propel the merged black hole out of its galaxy entirely, sending it hurtling into intergalactic space at thousands of kilometers per second. What's left behind is a galaxy without its anchor, and a black hole wandering the cosmos with no stars to call its own. If this happened to QSO-1, then its brilliance might be the result of it still carrying with it some of the gas it once fed on within its original galaxy. Even without a galactic home, a black hole can continue to shine if it has an accretion disk of gas spiraling around it. Over time, however, a rogue black hole would eventually consume or lose this fuel, fading into darkness. But QSO-1, being so luminous, suggests that if it was ejected, it happened relatively recently on cosmic timescales. It could be in the middle of a fleeting but spectacular phase, a black hole exiled into the void, still burning with the remnants of its stolen feast. The wandering black hole scenario also explains why no galaxy is visible around QSO-1. If it was ejected with extreme velocity, it could be millions of light years away from the galaxy that birthed it. Its gravitational tether to that galaxy would be severed, leaving it to drift through intergalactic space. To Webb's instruments, QSO-1 would therefore appear naked, bright and blazing, but without the galactic context we expect. The absence of a host galaxy, in this view, is not because it never had one, but because it lost it in the violent aftermath of a cosmic collision. This idea also finds support in the chaotic environment of Abell 744. The cluster is notorious for its history of galactic collisions and mergers, its landscape shaped by immense gravitational interactions over billions of years. It is, in a sense, the perfect place to look for ejected black holes. When multiple galaxies crash together, their central black holes are drawn into complex dances, sometimes resulting in ejections powerful enough to cast them out into intergalactic wilderness. If any region of the cosmos could produce a wandering supermassive black hole, Abell 744 would be it. QSO-1 might therefore be less an anomaly and more a natural byproduct of the cluster's violent history. Yet, as compelling as this explanation is, it comes with its own puzzles. A black hole ejected from its galaxy would still need a way to remain active. Typically, once cast adrift, such black holes are expected to go dark, starved of the dense gas and stellar material that fuel their accretion disks. QSO-1, by contrast, is blazing like a quasar, one of the brightest phenomena in the universe. For it to shine this brightly, it must still have access to an extraordinary amount of fuel. Perhaps it carried with it a disk of matter from its former galaxy, or perhaps it is traveling through a particularly dense pocket of intergalactic gas. Either way, it raises the question, how long can such a naked exile continue to burn before its light is finally snuffed out? If QS01 truly is a wandering black hole, then it opens up a haunting new possibility. The universe may be full of such exiles, drifting unseen in the darkness. For every one we catch blazing in a quasar-like phase, there could be countless others that have already gone dark, invisible, except for the faint distortions they cause in the fabric of space-time. Astronomers have speculated that there may be millions of rogue black holes in our own galaxy alone, each the remnant of collisions and gravitational kicks. QS01 could be the first time we've clearly seen one in its luminous active state, caught in the act of wandering, not yet faded into silence. And so, possible explanation 2 transforms QS01 into a story of violence and exile. It may once have been the beating heart of a galaxy, only to be cast out into the void by forces so immense that they defy imagination. Now, it wanders nearly alone, blazing defiantly in the darkness, a reminder that even the universe's most powerful giants are not immune to chaos. If this is the truth, then QS01 is not a paradox, but a revelation of cosmic brutality. Proof that the universe's evolution is not just about creation and growth, but also about destruction and banishment on scales we are only beginning to comprehend. A third possibility, and one that many astronomers keep open with cautious humility, is possible explanation 3. Maybe QS01 does have a galaxy wrapped around it, but that galaxy is so faint, diffuse, or unusual that even the James Webb Space Telescope cannot yet see it. This would mean that QS01 is not truly naked at all, only clothed in shadows too fine for our instruments to detect. It is a more conservative explanation, one that preserves the link between black holes and galaxies, but it also forces us to reckon with the extraordinary limits of observation, even with a machine as powerful as Webb. There are reasons to consider this possibility seriously. Galaxies in the early universe were not like the grand spirals and massive ellipticals we see around us today. Instead, they were often tiny, irregular, and clumpy, containing only a fraction of the stars of modern galaxies. Many were faint enough that they barely registered in telescopes even before cosmic redshift stretched their light to near invisibility. Webb, with its unparalleled infrared vision, was built to overcome this barrier, yet even it has limits. It is entirely plausible that QS01 sits within a faint, skeletal galaxy that is effectively drowned out by the brilliance of its central black hole. The quasar-like glow of accretion can easily outshine the surrounding galaxy by orders of magnitude, masking the faint starlight in the glare. This problem has plagued quasar studies for decades. Even relatively nearby quasars often appear as point sources, their galaxies invisible beneath the blinding central beacon. It is only with sophisticated techniques, subtracting the light of the quasar, stretching imaging data, or using specialized instruments, that astronomers can sometimes tease out the faint outline of the host. If QS01 is surrounded by a faint galaxy, the challenge is amplified by distance and time. At more than 13 billion light-years away, any starlight from its host galaxy would be stretched to infrared wavelengths and dimmed to near silence. The glare of the quasar would swamp it entirely. In this sense, QS01 might not be naked at all, just dazzling enough to conceal its clothing. If this explanation is correct, it would mean that QS01 is not rewriting the cosmic story so much as testing the very edge of our observational ability. It would remind us that even Webb, with all its revolutionary power, cannot pierce every veil. The faint galaxies of the early universe might be even fainter and more elusive than we imagined, requiring not just Webb, but future generations of telescopes, such as the Extremely Large Telescope, ELT, or the Nancy Grace Roman Space Telescope, to finally reveal them. QS01 then would become a symbol not of broken theory, but of the cosmos taunting us with mysteries just beyond our reach. But even this conservative explanation does not erase the puzzle. For QS01 to have a galaxy, that galaxy would still need to be unusually small and faint compared to the size of its black hole. The balance between galaxy mass and black hole mass is one of the strongest correlations in astrophysics. Typically, galaxies must be billions of solar masses and stars to sustain a central black hole of tens of millions of solar masses. If QS01's galaxy is so faint that Webb cannot detect it, then it must be disproportionately tiny compared to its black hole. This imbalance itself would break expectations. Instead of the black hole and galaxy growing in tandem, as theory predicts, QS01's black hole would vastly outstrip its host, dominating the relationship in ways we have never seen before. In fact, such a scenario could hint at a new class of objects, black hole-dominated galaxies, where the central singularity is not a resident of a galaxy, but its overlord, so massive that the surrounding stars are little more than a footnote. If QS01's galaxy exists, but is too faint to see, it may represent this kind of extreme imbalance, a cosmic partnership where one half has grown so large that the other is barely visible. That would still require rethinking the story of galaxy black hole coevolution, for it would show us that the relationship is not always equal. Sometimes the black hole takes the lead, dragging the galaxy behind it like an afterthought. There's also the possibility that QS01's invisible galaxy is hidden not by faintness, but by cosmic dust. Dust in the early universe was plentiful, the byproduct of exploding stars enriching space with heavier elements. Thick clouds of dust can obscure starlight while allowing infrared light from black hole accretion to shine through. Webb is designed to penetrate dust better than any previous telescope, but even it has limits when the dust is dense enough. QS01's faint host could therefore be smothered in dust, hiding its stars from our view. If this is the case, then QS01 is not a naked black hole at all, but a cloaked one, its galaxy hidden beneath veils of cosmic smoke. This possibility, though less radical than the others, carries its own philosophical weight. It highlights the humility of astronomy, the recognition that sometimes what we call anomalies may simply be limitations of our tools. The universe has no obligation to reveal all its secrets to us at once. It may dangle mysteries like QS01 just at the edge of detectability, forcing us to build ever more powerful instruments to chase them. If QS01's galaxy exists, but lies hidden from even Webb, then it becomes a challenge, a dare from the cosmos to push our technology further and sharpen our gaze. And yet, even in this explanation, the mystery is not diminished, it is transformed. Whether QS01 is truly naked or simply shrouded in faintness, its presence in the early universe is extraordinary. Its black hole is still far too massive, its timing still too early, and its brightness still too astonishing to fit comfortably into existing theory. A faint galaxy would answer part of the riddle, but leave the rest unsolved. QS01 would still be a cosmic puzzle, only slightly reframed. Not a naked giant, but a cloaked one, whispering that even the brightest discoveries can hide truths in their shadows. Thus, possible explanation 3 preserves the traditional link between galaxies and black holes, but at a cost. It requires us to accept galaxies far fainter and stranger than expected, or to acknowledge that the black hole-galaxy relationship is not as balanced as we believed. In the end, whether QS01 is truly naked or merely hidden within a ghostly galaxy, it still stretches the limits of our understanding. It still forces us to admit that the universe is deeper, darker, and more complex than even Webb's golden eyes can fully reveal. The implications of QS01's existence are nothing short of enormous. If black holes can truly form or survive without galaxies, then everything we thought we knew about the architecture of the cosmos is suddenly incomplete. Our current models of cosmic evolution are built on the assumption that galaxies are the fundamental building blocks of the universe. They are the cosmic cities, the cradles of stars, the scaffolding within which black holes form and grow. But QS01 challenges this idea at its core, suggesting that galaxies may not be the exclusive birthplaces of giants. Instead, black holes might be able to exist independently, as primordial structures or as exiles from violent collisions. If this is the case, then the story of the universe is not one of galaxies first and black holes second, but of multiple pathways of creation running side by side. This possibility would radically reshape our understanding of how structure emerged after the Big Bang. In the conventional picture, the early universe was filled with vast clouds of hydrogen and helium. These collapsed into the first stars, which then clustered into galaxies. Inside those galaxies, the first small black holes were born from dying stars. Over billions of years, these black holes merged and fed until they became supermassive. But if QS01 is truly alone, then it suggests that some black holes skipped the slow, galaxy-dependent route entirely. Perhaps they were born massive, through direct collapse, or perhaps they were violently ejected from galaxies and survived in isolation. Either way, it means that our models do not capture the full spectrum of possibilities. Cosmic evolution may be more diverse, chaotic, and non-linear than we imagined. The consequences ripple outward into almost every corner of astrophysics. For one, it challenges the long-held M-sigma relation, the tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of its stars. This relationship has been considered nearly universal, suggesting a deep coevolution between galaxies and black holes. But if QS01 exists without a galaxy, then this relationship is not as fundamental as we thought. It may be statistical rather than physical, a pattern that describes most cases but leaves room for dramatic exceptions. In other words, galaxies and black holes may often grow together, but they don't have to. The implications also extend to the timeline of the universe. If black holes can form without galaxies, then they could have appeared much earlier than we assumed. They might even predate the first galaxies, shining as luminous quasars in the dark universe before starlight filled the cosmos. This could help explain why astronomers have found so many quasars in the early universe, objects that seem impossibly massive for their age. If galaxies were not a necessary step, then black holes could emerge rapidly and independently, populating the universe with giants long before galaxies had the chance to stabilize. There are also profound consequences for our understanding of galaxy formation itself. If black holes can exist without galaxies, then perhaps galaxies formed around black holes, not the other way around. In this inverted view of cosmic history, black holes are not the products of galaxies, but the seeds from which galaxies grow. Their immense gravity could draw matter into dense regions, catalyzing the formation of stars and shaping galaxies in their wake. If this is true, then black holes are not secondary players in the story of the universe. They are the primary architects, the unseen hands guiding the assembly of cosmic structure. QS01 may be our first glimpse of this deeper truth. The discovery also impacts the search for other hidden populations of black holes. If one naked or nearly naked black hole can be found, there could be countless more scattered across the cosmos. Some may still be blazing with quasar-like light, but others may have gone dark, invisible, except for the gravitational effects they exert on their surroundings. This raises the possibility that the universe is filled with rogue black holes, wandering between galaxies, shaping cosmic environments in ways we have not yet detected. QS01 may therefore be the tip of an iceberg, the visible part of a much larger population that has gone unnoticed until now. The implications even extend into the realm of cosmology and physics. Black holes are not just massive objects. They are laboratories of extreme gravity, where the laws of physics bend to their limits. If they can exist independently of galaxies, then they may have played roles in the universe's history that we have not yet considered. They could have contributed to reionization, shaped the distribution of matter on cosmic scales, or even influenced the rate of cosmic expansion in subtle ways. By existing outside the neat framework of galaxy growth, they may be reminders that the universe's evolution is governed not by simplicity, but by complexity. And perhaps this is the greatest implication of all, that the universe is not a finished puzzle waiting for us to fit in the last few pieces. It is a living, evolving enigma, filled with surprises that will continue to defy us no matter how advanced our tools become. QS01 is not just an astronomical discovery, it is a reminder of the incompleteness of human knowledge. It forces us to face the fact that we are still beginners in the art of understanding the cosmos, and that the universe will always have the power to shock us, to humble us, and to expand the horizons of what we believe possible. The discovery of QS01 reopens a question that strikes at the very foundation of cosmic architecture: galaxies versus black holes. For decades, the dominant view has been that galaxies came first. They formed as vast clouds of hydrogen and helium, collapsed under gravity, giving birth to stars. Only later, when the most massive of those stars lived out their brief, fiery lives, did they collapse into black holes. Over time, these black holes merged and grew, eventually producing the supermassive giants we find at the centers of galaxies today. In this traditional framework, black holes are the byproducts of galaxies, a consequence of galactic evolution, not a cause. But QS01 forces us to entertain a radical inversion. What if black holes didn't just grow inside galaxies? What if they helped build them? Instead of being the children of galaxies, perhaps black holes were the parents, shaping galaxies from the very beginning. In this scenario, the immense gravity of early black holes could have acted as seeds, pulling matter into dense regions where stars could form. Galaxies may not have created black holes. Black holes may have been the gravitational scaffolding that allowed galaxies to assemble in the first place. There is already some evidence to support this reversal. Astronomers have long been puzzled by how tightly correlated the mass of a galaxy's central black hole is with the mass of the galaxy's bulge. The relationship is so precise that it suggests an intimate connection between the two. But correlation does not imply causation. While we often assume galaxies control black hole growth, it is equally plausible that black holes exert a commanding influence over galaxy growth. By pouring energy into their surroundings through jets, winds, and radiation, black holes can regulate star formation, preventing galaxies from becoming too large or too small. In this light, black holes may be not just passengers in galaxies, but cosmic engineers ensuring that galaxies form within certain limits. QSO-1 makes this idea even more tantalizing. If it truly exists without a visible galaxy, then perhaps we are catching a black hole in the act of building its own galactic home. Its immense gravity would naturally attract gas, dust, and dark matter, creating the conditions for stars to form. Over time, these stars could assemble into a faint galaxy, one that Webb may not yet be able to detect. In this view, QSO-1 is not incomplete. It is simply at an earlier stage of the galaxy building process. The galaxy may not be missing, it may just be under construction, a work in progress guided by the gravitational blueprint of its black hole. This flips our entire perception of cosmic chronology. For years, we thought of galaxies as the stage and black holes as the actors. But what if the opposite is true? What if black holes laid down the stage, set the scene, and galaxies were merely the structures that grew in response? QSO-1's existence makes this scenario plausible, even likely. It is as though the universe placed a glowing clue in front of us saying, "You have misunderstood the order of creation." The implications ripple outward into our understanding of cosmic evolution. If black holes helped build galaxies, then the first billion years of the universe may have looked very different from what our simulations suggest. Instead of fragile, star-dominated galaxies struggling to grow, the early cosmos may have been dotted with black holes like QSO-1, each acting as a gravitational hub. These hubs would have drawn in matter, ignited star formation, and ultimately sculpted the galaxies we see today. The universe's grand architecture, from the smallest galaxies to the largest clusters, may therefore owe more to black holes than to galaxies themselves. This also changes how we think about the role of feedback, the energy black holes release into their surroundings. In the traditional view, feedback is a byproduct of black holes growing inside galaxies. But if black holes came first, feedback may have been the mechanism that determined what galaxies could become in the first place. QSO-1's blazing quasar-like light is feedback in action. Radiation powerful enough to heat surrounding gas, prevent runaway star formation, and regulate the size of any galaxy that might form around it. In this sense, black holes may have acted as the architects of balance, ensuring that galaxies never grew unchecked. Philosophically, the question of galaxies versus black holes also touches on our assumptions about hierarchy in the universe. We like to think in terms of building blocks. Particles build atoms, atoms build stars, stars build galaxies, and galaxies build black holes. QSO-1 challenges this linear logic. It suggests that the cosmos may not follow a tidy ladder of progression, but instead weave a more complex web, where sometimes the supposed endpoints of evolution become the starting points. Black holes may not be the final products of galactic evolution. They may be the seeds from which cosmic order itself emerges. And if that is the case, then QSO-1 is not an exception. It is a revelation. It shows us that black holes may hold a more fundamental role in the universe than galaxies, stars, or even dark matter. They may be the keystones of cosmic architecture, the hidden hands that shaped the universe into what we see today. In the battle of galaxies versus black holes, QSO-1 tilts the balance in favor of the giants of gravity, reminding us that what we thought were mere consequences may in fact have been the causes all along. QSO-1 represents more than a fascinating anomaly. It is a challenge to theory, one so direct and unrelenting that astronomers cannot simply file it away as an outlier. This single discovery forces us to confront the possibility that our most trusted frameworks for understanding galaxies and black holes are incomplete, or perhaps fundamentally flawed. For decades, the relationship between galaxies and their central black holes has been treated as a cornerstone of modern cosmology, a tidy story in which the two co-evolve, growing in tandem and regulating one another's development. But QSO-1 cuts across that narrative like a blade. Here is a black hole that appears naked, without a visible galactic host, existing at a time when galaxies were supposed to be fragile infants. It is as if the universe itself is telling us, your assumptions are not enough. The heart of the challenge lies in the coevolution model. Observations of nearby galaxies show a striking correlation between the mass of a galaxy's central black hole and the properties of the galaxy's bulge. The larger the galaxy, the larger its black hole. This consistency seemed too strong to be coincidence, and so the idea took hold that galaxies and black holes grow together in lockstep. Feedback from black holes, in the form of radiation and powerful jets, regulates star formation in galaxies, while galaxies feed their black holes with gas and stars. It was a neat, reciprocal dance, one that gave structure to the story of cosmic evolution. But QSO-1 doesn't fit into this dance. Its black hole is enormous, 50 million solar masses, yet no galaxy is visible around it. If the coevolution model were absolute, this would be impossible. Either the galaxy should be massive enough to match its black hole, or the black hole should be far smaller to match the absence of a host. Instead, QSO-1 exists in a state of defiance, its presence a clear contradiction of the rules we thought governed the cosmos. One object alone is enough to shake an entire framework, because if it can happen once, it can happen again. And if it happens often, then the model is not a universal law but a partial description. This challenge extends beyond the relationship between galaxies and black holes. It destabilizes our understanding of the timeline of structure formation. The idea that galaxies must form first, and that black holes grow inside them provided a logical sequence of events that explained much of what we see today. But QSO-1 forces us to consider alternatives, that black holes may sometimes form first, or that they may grow in isolation before galaxies assemble around them. This flips our cosmic chronology and demands new models that account for multiple possible pathways. Instead of one linear story, the universe may tell many overlapping stories, with black holes and galaxies trading roles as cause and effect depending on the circumstances. The discovery also challenges the limits of black hole growth. According to current theory, black holes are constrained by the Eddington limit, the maximum rate at which they can consume matter without blowing it away with their own radiation. For a black hole to grow to QSO-1's size in less than 1 billion years, it would have to either feed at rates far above this limit, or begin life already massive through direct collapse. Both scenarios strain existing models. If the Eddington limit can be broken under certain conditions, then our understanding of accretion physics must be revised. If direct collapse is more common than we assumed, then the early universe may have been seeded with giants we have only just begun to detect. The challenge is not only scientific, but also philosophical. Astronomy has always sought patterns, rules, and universal laws that bring order to the cosmos. The galaxy-black hole relationship was one such law, a comforting symmetry that explained both the small and the large. QSO-1 reveals that the universe is under no obligation to maintain such symmetry. It reminds us that what we call laws may be statistical trends, not absolutes. The cosmos is not a machine running on simple gears, but a living system filled with exceptions, extremes, and surprises. QSO-1, by its very existence, demands that we embrace this complexity rather than reduce it. At the same time, the challenge of QSO-1 is invigorating. Science advances not when discoveries confirm our expectations, but when they shatter them. Each contradiction is an opportunity to learn, to refine, to expand our view of what is possible. QSO-1 forces astronomers back to the drawing board, prompting new simulations, new theories, and new predictions. Already, researchers are re-examining old data, searching for other objects like it, and pushing Webb to probe deeper into regions of the sky where hidden giants might lurk. Theories of black hole seeding, galaxy formation, and accretion physics are all being re-evaluated in light of this single discovery. And perhaps that is the greatest testament to QSO-1's importance. It is not just an object in the sky, it is a turning point, a reminder that the universe is always stranger than we imagine. This one discovery forces us to rethink the relationship between galaxies and black holes, to consider new models of evolution, and to admit that our frameworks are, at best, approximations of a reality far more intricate than we can yet grasp. In challenging our theories, QSO-1 fulfills the deepest purpose of science: to confront the unknown, to question the known, and to push us toward truths we cannot yet see. The discovery of QSO-1 did not end with a gasp of shock. It lit a fire. Once astronomers realized that the James Webb Space Telescope had uncovered what appears to be a naked or nearly naked supermassive black hole, a new question immediately took shape. If JWST found one, how many more might be out there? The cosmos is vast beyond comprehension, and Abell 2744 is only a small patch of sky. If a single deep observation revealed QSO-1, then logic suggests it may not be unique. Instead, it could be the first of a hidden population, a class of objects waiting silently for us to notice them. This idea has expanded the search, transforming QSO-1 from an isolated enigma into a potential herald of a new era in black hole discovery. The James Webb Space Telescope, with its golden mirrors and infrared vision, is designed to see deeper into space and farther back in time than any telescope before it. Its instruments can detect the faintest whispers of light stretched across billions of years. That means Webb is uniquely equipped to uncover objects like QSO-1, which might have gone unnoticed in past surveys. Already, astronomers are poring over Webb's datasets, scanning for other points of inexplicable brilliance, quasar-like objects in the early universe that shine without visible galaxies. The hunt has become systematic, with entire research teams combing through gravitational lensing fields, galaxy clusters, and deep sky surveys, hoping to find more naked giants hiding in the cosmic dawn. If even a handful of such objects are found, the implications will grow exponentially. QSO-1 could no longer be dismissed as a rare anomaly or statistical fluke. Instead, it would be part of a population of rogue or galaxyless supermassive black holes scattered throughout the early universe. Their existence would force us to fundamentally rewrite our models of structure formation. They could represent either a dominant mechanism for black hole growth in the early universe, or at the very least, a parallel evolutionary path that coexisted with the one we have long assumed to be standard. The possibility of a larger population also redefines how we think about the role of black holes in cosmic evolution. If many naked giants existed during the first billion years, then they may have shaped the universe in profound ways. Their intense radiation could have contributed significantly to the epoch of ionization, the period when the fog of neutral hydrogen cleared and the universe became transparent to light. They may have acted as gravitational wells that accelerated the clumping of matter, helping to sculpt the first large-scale cosmic structures. In other words, they may not have been rare curiosities, they may have been architects of the early cosmos. The search also extends beyond the early universe. If black holes can be naked in their youth, then some may survive into the present day, wandering through intergalactic space without hosts. Detecting them directly would be far more difficult, since without accretion disks or surrounding galaxies, they would emit little to no light. But their gravitational effects could still betray their presence, through microlensing events, distortions in galactic motions, or even the ripples of gravitational waves they generate when colliding with other black holes. QSO-1 has therefore widened the scope of black hole research, pushing scientists to think not only about what exists in the distant past, but also about what invisible giants may haunt the present universe. Philosophically, the expanding search underscores one of science's most powerful lessons. One discovery is never just one. A single anomaly becomes a spark that ignites entire fields of investigation. QSO-1 is not simply a lonely puzzle. It is a clue, a signpost pointing to deeper mysteries. If Webb can uncover one naked giant, then it can uncover others, and each one we find will add to the tapestry of cosmic understanding, revealing whether QSO-1 is a rare exception or the first representative of an unseen majority. The excitement is palpable in the astronomical community. Proposals for Webb's observing time are increasingly aimed at identifying other naked or near-naked black holes. Simulations are being run on supercomputers, testing how populations of such objects could form, evolve, and influence their environments. Already whispers of possible candidates are emerging from Webb's datasets, sources that look suspiciously similar to QS01, awaiting confirmation through deeper analysis. The search has begun in earnest, and each discovery will either reinforce or transform our picture of the universe's first billion years. And so, the story of QS01 is not confined to a single black hole. It has opened the door to a new era of exploration, one in which we must scan the skies for more hidden titans blazing against the dark. The search expands with every Webb observation, every dataset analyzed, every anomaly flagged. If QS01 is not alone, then the universe is even stranger and more abundant in surprises than we dared to hope. What was once a solitary enigma may soon become the first chapter in a story of countless naked giants, each one a reminder that the cosmos always holds more than we expect. The discovery of QS01 reminds us of a profound truth. We live in a universe of surprises. Each time the James Webb Space Telescope captures a new image, it proves that the cosmos is not the predictable, orderly system we once imagined, but a wild, complex, and often baffling reality that defies our expectations at every turn. Webb was built to sharpen our view of the universe, to give clarity where Hubble had only hinted, but what it has delivered is far more disruptive. A steady stream of revelations that show us just how incomplete our cosmic story really is. From galaxies that formed sooner than theory allowed, to stars too massive for standard models, to anomalies like QS01 that challenge the very foundations of black hole physics. Every observation seems to whisper the same message: the universe is stranger than you think. QS01 is a perfect example of this strangeness. By all rights, it should not exist in the way that Webb has revealed it. Yet it does, blazing defiantly against the dark backdrop of the early cosmos. And QS01 is not alone in challenging our assumptions. Webb has uncovered galaxies that appear shockingly mature less than 1 billion years after the Big Bang. Galaxies that should not have had enough time to gather so many stars or to form such complex structures. It has revealed star-forming regions that are larger and more chaotic than we predicted, as well as planetary systems that test the limits of what we thought worlds could be. Each discovery is a reminder that our models are just sketches, not finished blueprints, and that nature is endlessly inventive in ways our theories cannot yet capture. This sense of surprise is not just about individual objects, it's about the cosmic order itself. We once believed the universe followed a neat progression: the Big Bang, the first stars, galaxies forming, black holes growing inside them, and structure building steadily over billions of years. Webb shows us a universe far messier, a universe where giants appear before their time, galaxies grow at breakneck speed, and the rules bend in ways we never expected. Instead of a simple ladder of progression, the cosmos looks more like a tangled web of overlapping pathways, each one producing marvels we can barely comprehend. And the surprises are not just confined to what we see, they extend to what we don't see. For every blazing quasar or luminous galaxy Webb captures, there are countless mysteries hidden in its shadows. Faint galaxies we cannot yet resolve, rogue black holes drifting invisibly, structures too subtle or too strange for our instruments to detect. Each image is not just a window into what we know, it's a reminder of how much remains concealed. The universe surprises us not only by what it reveals, but by what it withholds, daring us to build better tools, ask better questions, and imagine possibilities beyond the edge of our vision. What makes these surprises so powerful is that they are revolutionary, not incremental. They don't merely add detail to our models, they challenge the models themselves. QS01 does not fit neatly into the galaxy black hole framework. It breaks it. The early massive galaxies Webb has found don't refine our understanding of galactic growth, they overturn our timelines. Each surprise forces us to abandon the comfort of certainty and embrace the chaos of discovery. In this way, Webb has become not just a telescope, but a teacher, humbling us with the lesson that the universe is infinitely more complex than the equations we use to describe it. Philosophically, this universe of surprises is exhilarating. It reminds us why we look to the stars in the first place, not to confirm what we already believe, but to discover what we never imagined. Every shock, every contradiction, every enigma is a doorway to deeper understanding. QS01's existence tells us that black holes and galaxies may have a far more complicated relationship than we thought. The early massive galaxies tell us that the universe can build with astonishing speed. The exotic planetary systems Webb has revealed tell us that worlds can take forms we never dreamed of. Each surprise expands not just our knowledge, but our sense of wonder. And there is something deeply human in this process. We crave order, predictability, and explanation, but the universe offers us mystery, chaos, and revelation. Webb shows us that the cosmos is not a solved puzzle, but a living enigma, constantly evolving and constantly capable of astonishing us. This is not a failure of science, it is its greatest strength. To be surprised is to learn, to be humbled is to grow, and to be confronted with the unknown is to stand at the threshold of discovery. So, when we call QS01 strange, when we marvel at the early galaxies or puzzle over unexpected stars, we are not just cataloging anomalies, we are glimpsing the true nature of the universe. It is stranger, wilder, and more complex than we imagined, and it always will be. Each Webb image is not the end of a search, but the beginning of countless new ones. Each surprise is not a contradiction, but an invitation to look deeper, to think bigger, and to accept that the cosmos will never stop revealing wonders that leave us in awe. In the end, the story of QS01 leaves us with a profound closing reflection. In the depths of time and space, James Webb revealed a supermassive black hole that seems to exist outside of every order we thought governed the cosmos. It is not merely another bright spot in the sky or a curious quasar among many. It is a defiance written in light, a cosmic contradiction that refuses to fit neatly into our models. QS01 is both a discovery and a disruption, a reminder that for all we have learned about the universe, it still holds mysteries far beyond human expectation. There is something poetic in this revelation. For generations, humanity has looked to the stars searching for answers, imagining that with each leap in technology we would come closer to a final, complete understanding of the cosmos. The James Webb Space Telescope, with its golden mirrors and extraordinary vision, was often portrayed as the key that would unlock the last secrets of the early universe. And yet, instead of closure, it has delivered confusion. Instead of certainty, it has given us paradox. QS01 is proof that the universe does not simply yield to our desire for neat explanations. It remains untamed, full of surprises that demand we rethink everything we thought we knew. This black hole, 50 million times the mass of our sun, shining in the early universe without a visible galaxy, is not just an object of science. It is a symbol of humility. It tells us that the cosmos is far older, stranger, and more inventive than the frameworks of our minds. The order we impose, the narratives we build, are only shadows of a reality too vast for us to fully contain. Every time we believe we have written the story of creation, the universe adds a new chapter, one that forces us to reconsider the plot entirely. And perhaps that is the true gift of QS01, not the answers it provides, but the questions it leaves behind. Was it born from the direct collapse of a gas cloud, skipping the steps of stars and galaxies? Was it cast out of a galaxy during a violent collision, now blazing in exile? Or does it sit within a galaxy so faint, so ghostly, that even Webb cannot yet reveal it? Each possibility reshapes our vision of the cosmos, and each invites us to keep searching. QS01 is not an endpoint. It is a beginning, a signpost pointing toward mysteries that lie deeper still. As we reflect on this discovery, we must remember that astronomy is not about certainties. It is about wonder. The telescope does not give us the comfort of final truths. It gives us the thrill of endless mystery. QS01 is a silent reminder that the universe is not a puzzle waiting to be solved, but a living enigma that will always stay one step ahead of us. To look into its depths is not to find closure, but to be reminded of how much more there is to learn. And so, in the faint light of a black hole that should not exist, shining from a time when the universe was still young, we find ourselves confronted with the infinite. Webb has shown us not just a supermassive black hole, it has shown us our own smallness, our own humility, and our own capacity for wonder. QS01 defies order, but in its defiance, it points us toward the truth, that the cosmos is still writing its story, and we are only just beginning to read it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.